So last time we stopped with a discussion of rotations, and also I start talking about Lorentz boosts. So let me briefly repeat the main points of the last discussion. So we consider three-dimensional rotations, and three-dimensional rotations are given by such elements which explicitly are 3 by 3 matrices. So indices I and J runs from 1 to 3, and they are cosine theta delta ij plus 1 minus cosine theta ni and j minus sine theta epsilon ijk multiplied by nk. And over repeated index k, there is a summation here. And these matrices, you can check that they are orthogonal. So R transpose R is equal to R transpose is equal to 1. And they are periodic in theta. So if you shift theta by 2 pi, then the matrix returns, matrix elements return to themselves. So n theta plus 2 pi is equal to R n theta. And these are three-dimensional rotations, and they embed into a six-dimensional Lorentz group in the following way. So matrix lambda, which is a matrix of Lorentz transformation, which is in this case a rotation, is constructed in the following way. You take identity, you just take 1 here, and then 3 zeros, 0, 0, 0 here, 0, 0, 0 here. And on this block, you put R on n theta, which is our 3 by 3 dimensional matrix. So this is 3 by 3 block here. So this is matrix of Lorentz transformation, which is a rotation. Now, what about Lorentz boosts? I said that in that case, we have to consider a similar parameterization of boosts. Instead of 3 by 3 matrices AI, we need to consider 3 4 by 4 matrices BI. And last time I have written down explicitly their form. And again, exponentiating these matrices, but now multiplied with the angle var theta multiplied by n by b, we will get a matrix of Lorentz boosts. So this will be Lorentz boosts. And explicitly, if you perform the corresponding exponentiation, you will find the following matrix. So n var theta will be given by cosh var theta minus ni sinh var theta, here minus ni sinh var theta, and here delta ij plus cosh var theta minus 1 ni and j. So this is 4 by 4 matrix, and it is parameterized now by the hyperbolic angle and the name hyperbolic is related, of course, with the appearance here, hyperbolic functions, cosh and sinh. And the angle, hyperbolic angle var theta is not now running on a compact space from 0 to 2 pi, but it runs actually from minus to plus infinity. The variable var theta, for this reason, is usually called rapidity because it will be related to a velocity with which we boost our Lorentz system with respect to the reference system. So rapidity, that's the name for this variable, rapidity. Now, if we want, first of all, you see that cosh var theta is always bigger than 0. Actually, it's bigger than 1, bigger or equal to 1 by the property of cosh. It's a variable which takes values from 1 to plus infinity. And for this reason, you can parameterize it in a more conventional way as cosh var theta is equal to 1 divided by square root of 1 minus v squared divided by c squared, where v is a velocity vector, three-dimensional velocity is a velocity vector. So rapidity is related to velocity by means of this formula. So rapidity is a scalar variable, while velocity is a three-dimensional vector, and this is a relation. Cosine var theta is given by 1 divided by square root 1 minus v squared divided by c squared, where c is the speed of light. Now, these transformations, as you understand, they now correspond, as you see from this formula, to the orthochronous transformations. And this is because cosh var theta is bigger or equal to 1. Clearly, this means that the component lambda 0, 0 of the Lorentz transformation we are considering here, this one, is bigger than 0. And once it's bigger than 0, this means that we are dealing with orthochronous Lorentz transformations. This equation here can be solved for the modulus of velocity. And if you do that, then you find the following answer. So modulus of v is given by plus minus c multiplied by hyperbolic tangent of the rapidity variable. And in order to have orthochronous transformations, what we can do, let's take here just one of these possibilities. So a plus sign. So if you choose a plus sign, not minus, but plus, in this case, it is clear that we have to restrict the variable var theta to run from 0 to infinity, right? Because in that case, tangent will be positive, and you will get on the right-hand side the non-negative expression. And in this case, if you make this choice, then you see that the variable sinh of var theta will be given by modulus of v divided by c square root of 1 minus v squared divided by c squared. So in other words, we uniquely solve for sinh of var theta, and now we can use this parameterization of cosh and sinh in our formula for Lorentz transformation lambda. So let's substitute these formulas inside our expression for lambda. And in this way, we will get the following expression. So now I'm doing this substitution and see what I get. I get the following answer. I will get the following answer. Lambda is now parameterized, will be parameterized by a three-dimensional vector V. And this is 4 by 4 matrix, which has the following structure. Here I have square root 1 divided by V squared divided by C squared. Here I will have minus 1 divided by square root 1 minus V squared divided by C squared multiplied by V divided by C, where V now is a three-dimensional vector. And this three-dimensional vector, V, is obtained by multiplying modulus of V by the direction vector n. So this vector quantity V appears because we have a three-dimensional unit vector, but now we multiply it by the modulus of V, and this gives us the vector V itself. Now, here we will have minus 1 divided by square root 1 minus V squared divided by C squared, V transpose divided by C. So this is a three-dimensional row. And finally, in this part of our matrix, we will have three-dimensional identity matrix, 3 by 3 identity, plus 1 divided by square root 1 minus V squared divided by C squared, minus 1. And here, V tensor V transpose divided by V squared, and then the bracket is closed. So this is a matrix representing Lorentz boost. Lorentz boost. And V is the velocity with which we boost our moving frame with respect to the original inertial frame. Expression here, V multiplied by V transpose, should be understood in the following way. So we have column V1, V2, V3, and we multiply it in a tensor way by a row V1, V2, V3. And the rule of tensor multiplication means that we take, say, component V1 and multiply it successively by V1, then by V2, and then by V3, and then we do the same with component V2, and then we do the same with component V3. So to write this in terms of matrix elements, V transpose is a 3 by 3 matrix whose component ij is simply given by Vi Vj. This is a way to understand this 3 by 3 matrix. And identity, as I said, is 3 by 3 unit matrix standing there. Okay, so now we can formulate the general form of Lorentz transformations, namely the four-dimensional vector x prime is related to the vector x, original vector x, by a rotation matrix over axis n by angle theta, and also by a matrix of Lorentz boost depending on three-dimensional velocity vector. And this is applied to x. And so this is kind of a general or generic Lorentz transformation. So you have three parameters related to rotation and rotations, and three parameters encoded in this velocity vector related to Lorentz boost. So altogether, you have a 6-parametric group of transformations. And if you write this more explicitly, then you know what is x prime. X prime is a 4-dimensional vector whose zero component is ct prime. And then you have x prime 1, no, maybe it's better to write in this way. X 1 prime, x2 prime, x3 prime. And this primed vector is related to unprimed vector by means of a matrix of rotation here 0, 0, r, and theta. And then there is a matrix of Lorentz boost, this square root 1 minus v squared over c squared, minus 1 square root 1 minus v squared over c squared, v over c, here minus 1 divided by square root 1 minus v squared over c squared, v transpose over c, and finally this identity plus 1 square root minus 1 v transpose divided by c squared. No, and here these 4x4 matrices are applied to CT, x1, x2, x3. And if you now write this expression for components, just multiply the vector on the right-hand side by these two matrices, you can derive from here the individual, transformation loss for individual components of our four-dimensional vector. So for T prime, you find that T prime is related to the original coordinates by the following formula: T minus xv divided by c squared divided by square root 1 minus v squared over c squared. And x prime, three-dimensional vector x prime, is related to the original vector x and time t by the following formula: three-dimensional rotation matrix n theta acting on x prime minus vt divided by square root minus v squared over c squared plus 1 divided by square root 1 minus v squared c squared minus 1. And here v multiplied by a scalar product of v with vector x and divided by v squared. And so you may now recognize that what you see here are the standard formulas of special relativity for the transformations of time coordinate t and the spatial coordinates x prime, x, and under Lorentz transformations governed by the rotation parameters r and theta, and also by the velocity vector v. These are the standard formulas which you may recognize from your course on special relativity. As an exercise, what you may try to do, you may try to use these formulas, for instance, to derive the law of addition of velocities in special relativity. For that, you need to consider two successive Lorentz transformations, which are boosts, say with velocity v1 and v2, and use these formulas in order to see how actually velocity add in special relativity. You may do it as an exercise. Okay, any questions concerning Lorentz transformations?
Yeah, the particle's motion is in x-axis, right?
The particle motion is, I don't quite hear the last word which you said. The particle motion is, you said?
Is in x-axis, right?
Yeah.
And what can we say about, means how can we represent using this form for the orthogonal axis?
Yeah, you see, what you do here is that if you have a particle which in one Lorentz frame, it has coordinates x1, x2, x3, and the time t, then making a transformation to another Lorentz frame, in this other Lorentz frame, upon performing the Lorentz transformation, the particle will have coordinates or event or particle, whatever you call it, event will be described by coordinates t prime, x1 prime, x2 prime, x3 prime. And these formulas describe the transition from one coordinate system to the other coordinate system. So V here is a velocity not of a particle, but this is a velocity with respect to which you boost one Lorentz frame with respect to the other. You see, it's not a velocity. It's not a velocity of a particle itself. You just have a point or event in one Lorentz frame, and you see how the coordinates of this event are changed when you go to another Lorentz frame. Event is the one and the same, but you are changing the frame, and so coordinates of this event in a new frame will look different. And the transformation from one frame to another frame is in the fact that one frame may move with respect to the other frame uniformly with a velocity v. And this is this velocity which is present in this transformation. This is not velocity of a particle. This is a velocity with respect to which you boost one Lorentz frame with respect to the other. Okay?
Okay, got it.
Now, we can extend Lorentz group to Poincare group by including also shifts of space-time coordinates of the following form. So x prime mu goes, or x mu, better to say, x mu goes to x prime mu, which is x mu plus a constant shift a mu. So a mu is a constant four-dimensional vector. Now, let me know if you are familiar with the concept of a Lie algebra. Lie algebra. So Lie algebra is an important notion, which is related to the notion of a Lie group. And so Lie algebra, in a way, is an infinitesimal version of a Lie group. It's a very, very rough way to say this. Mathematically, a Lie algebra is a linear space which is supplied an operation called commutator, which is, this operation is bilinear, skew symmetric, and satisfies Jacobi identity. So in other words, a linear space which is supplied an operation commutator, which takes this space to itself, and which is skew symmetric. So if you apply it to two elements of a vector space, say V and W, it is minus WV. And it also must satisfy Jacobi identity. So if you take three such elements, VW, say, and U, and then you add up cyclic permutations, UVW plus WUV, then the result must be equal to 0. No, and this operation must be bilinear. Then such a linear space is called a Lie algebra. And in fact, every Lie group has a Lie algebra, and in particular, Poincare group has a Lie algebra. And this Lie algebra is spanned by generators, which I will denote by M mu nu, wherein this is now mu and nu run 0, 1, 2, 3. And this will be M mu nu will be Lorentz generators. And in addition to Lorentz generators, there will be also generators responsible for these shifts. For these shifts here, I denote them by P mu. These will be the generators called momentum. momentum generators or generators of momentum. We will see a little bit later that shifts, space-time shifts, they are related to momentum of our dynamical system, and so it's very natural to call this PMU also momentum generators. Now, the Lie algebra relations between these generators, which make a Lie algebra of the Poincare group, are given by the following commutation relations. So commutator of M mu with M rho sigma is written down via Minkowski metric, and generators M mu sigma plus eta mu rho M mu sigma plus eta mu sigma M mu rho minus eta mu sigma M mu rho. This one relation. There is one more relation which involves M mu nu with P sigma. This is I eta mu sigma P nu minus eta mu sigma P mu. And generators P commute between themselves. So if you have P mu, then these generators commute. So this is how Lie algebra of the Poincare group looks like. So the algebra of Poincare group. Exponentiating these generators of the Lie algebra, we will get the corresponding group elements. And in fact, we have already done this, for instance, for the case of the rotation group. We saw that we construct the group element R by means of exponentiating these matrices A, but these matrices A, they are elements of the Lie algebra of the rotation group SO3, and the corresponding commutator AI, AJ of these matrices is easy to compute, and we will find out that the formula will be epsilon ijk AK. So these three AIs form a Lie algebra, so they are, better to say, generators of the Lie algebra SO3. SO3 Lie algebra. And I'm discussing a general construction of the Lie algebra of Lorentz group and more generally Poincare group.
Excuse me, can you give me a reminder, how did we move from the Lorentz group to the Poincare group?
We just added, in addition to Lorentz transformations, we have added the shifts of the coordinates x mu. So Lorentz transformations were the transformations which are four-dimensional rotations. X prime mu is lambda mu nu x nu. And now we consider other type of transformations where x prime mu is equal to x mu plus constant shifts by A.
Okay,
and this is Poincare.
Yes. Okay, thank you.
We extend the Lorentz transformations by adding extra transformations of the coordinates, which are shifts, constant shifts. So altogether, this is Poincare transformations. Poincare transformations. Good. Now, let me just say one more thing, maybe to finish with this story about Lie algebra of the Poincare group. That in quantum theory, the Poincare generators become Hermitian operators. And in fact, this explains why there is an I here in these relations. Hermitian operators means that this M mu and P mu are represented as operators satisfying this condition. M mu dega, where dega is an operation of Hermitian conjugation, and P mu dega is equal to P mu. And these generators then will be explicitly realized on a certain space called the Fock space. We will come to the discussion of the Fock space a little bit later on, but you have to have in mind that this is a way, in principle, this is a way which we want, or this is a scheme which we want to achieve in quantum field theory. We want to find the so-called unitary, find and realize unitary representations of the Poincare group. And as you know, unitary representations in general, they play a very important role in quantum mechanics and also as a consequence in quantum field theory, because unitarity is naturally related to the conservation of probabilities. So in quantum field theory, we also want to achieve unitary representations of our symmetry groups. And one of the important symmetry groups is the Poincare group, which is a symmetry group of our space-time. And therefore, we will be aimed to obtain the unitary representation of this Poincare group. No, and finally, let me also explain or recall, if you know about this, the relation, important relation between the proper orthochronous Lorentz group, whose name is SO plus 1, 3. You remember, proper means determinant is equal to 1. Orthochronous means that these transformations preserve the direction of time, which is stressed by writing this plus here in the definition of SO plus 1, 3. And the relation between SO plus 1, 3 and their special linear group of complex 2x2 matrices, whose mathematical name is SL2C. So let me explain how these two groups are related. We have three Pauli matrices, sigma I. You know them, I think, very well from quantum mechanics. So there is a sigma 1, which is 0, 1, 1, 0. There is sigma 2, which is 0 minus I, 0. And there is sigma 3, which is 1, 0, 0, minus 1. Okay. These three Pauli matrices can be combined with the unit matrix, sigma 0, which is just a unit 2x2 matrix like this. And they can be combined in one definition of a matrix sigma mu in the following way. So sigma 0, sigma I. So when index mu is equal to 0, then you get sigma 0. When mu is 1, 2, 3, then you get one of the Pauli matrices. And simultaneously, you introduce the notion of matrices sigma bar mu, which is sigma 0 minus sigma I. So sigma mu and sigma bar mu are collections of 2x2 matrices. Then, having a 4-dimensional vector x mu, you define a 2x2 matrix, 2x2 Hermitian matrix. 2x2 Hermitian matrix by means of the following construction. Let's denote this matrix by x capital, and it's given by sum mu from 0 up to 4, x mu sigma mu. Or the same thing will be achieved if the same matrix will be constructed if you sum up from 0 to 4 eta mu nu x mu sigma bar nu. So here actually you need to sum over mu and nu. No, but since Minkowski metric eta mu nu is diagonal, the result of this summation will be actually diagonal, and you understand since components of the metric plus 1 minus 1, minus 1, minus 1. These minuses will be compensated by these minuses in the definition of sigma bar, and you will get the same result. And if you substitute here the matrix is sigma, then you see that explicitly you construct the 2x2 matrix of the following type, where the components of the 4-dimensional vector x mu, this will look like x0 plus x3, x1 minus I x2, x1 plus I x2, and here x0 minus x3. This is how this matrix X look like, and well, it's easy to see that since x mu are real, 4 real variables, then this matrix is Hermitian. Hermitian meaning that under Hermitian conjugation, it stays invariant. Okay. Other way around, if you have such a Hermitian matrix, then you can uniquely determine the original components x mu by taking a trace of x with a matrix sigma mu. More precisely, this is 1/2 trace x capital multiplied with sigma mu. This is how the formula looks like. And you can easily verify that computing such a trace, you will return back to the original coordinates x mu. Finally, you see also that if you compute the determinant of this Hermitian matrix X, you see this will be x0 minus x3 squared, x0 plus x3 multiplied by x0 minus x3 minus x1 minus I x2 x1 plus I x2. So if you open this up, then you see that this will be x0 squared minus x1 squared minus x2 squared minus x3 squared, which is nothing else as a 4 interval, Lorentz invariant 4 interval. 4 interval. So determinant of x is just a 4 interval constructed via coordinates of the vector x mu. Now I can define on this Hermitian matrix X the action of the group SL to C. So let's take a matrix G from SL to C and allow it to X on our Hermitian matrix X in the following way. X goes to X prime, where X prime is defined as G X G dagger, where dagger means Hermitian conjugation. Well, it's clear that such a transformation, first of all, will not destroy hermeticity. It preserves hermeticity, because if you take Hermitian conjugation, due to the rules of Hermitian conjugation, you will get Gx G dagger dagger, and then you will get G dagger dagger here, X dagger G dagger, and dagger dagger is give you G back. X is Hermitian, and so you see that then you return to X itself. So hermeticity is preserved. Now you see also that if you look at the determinant of X prime, then this is determinant of Gx G dagger, which is due to the property of the determinant of G multiplied by determinant of G dagger multiplied by determinant of X. Determinant of G dagger is determinant of G transpose, but determinant under transposition does not change, and then conjugate. But since we are talking about special linear group, determinant of G is equal to 1 by the definition of what we call special linear group. This is a group of 2x2 complex matrices with a unit determinant. We conclude that since these determinants are equal to 1, we get determinant of x, and determinant of x is a 4 interval. 4 interval. From where we conclude that such transformations by matrices from SL to C, they preserve the 4 interval. And once they preserve the 4 interval, we say that what they do, they just perform on the vector x mu Lorentz transformations. Lorentz transformations, right? Because Lorentz transformations are transformations which preserve, by definition, the 4 interval. And our transformations we are performing here with an elements of GL to C, SL to C, sorry, these are transformations which preserve the 4 interval. They can be found.
Professor,
Yeah.
can we say it theoretically like this because length is conserved, so that's why, or however we transform it, it will be conserved in another frame also.
Yeah, so length of this vector x is conserved. Yes, indeed. The length of the vector is conserved, and this is a definition of a Lorentz transformation, right? And so we see that conservation of length is guaranteed by this transformation. So these transformations actually realize an action of a Lorentz group on our 4-dimensional vectors x. It's just built up in this very funny way, right? Now as gx g dagger.
Yeah.
But we can write this transformation more explicitly. Yes, there was a question. Mm-hmm.
Yeah.
We can write it more explicitly. So we say x prime mu. What is this? This is 1/2 trace of x prime of this Hermitian matrix X transformed multiplied by sigma mu. So this is, I refer to the way of restoration back x mu from Hermitian matrix X. And so transformed coordinates will be restored via transform matrix X in this way. And then we can substitute here explicitly what X prime is. So this is Gx G dagger sigma mu, like this. Then what we can do, we can substitute here the definition of X by using the matrix sigma bar. So to write this as 1/2 trace sigma mu G sigma bar rho G dagger eta rho nu x nu. So what I have done, I've just substituted here for x the formula which expresses this x. Here it is, maybe I not here, which expresses it via original coordinates, x nu. And so this formula relates the transformed coordinates to the original coordinates, and we know how this transformation should look like in terms of matrix of Lorentz transformation lambda mu nu x nu. So this means that I found this matrix in an explicit way. It's given by this formula here. In other words, the matrix lambda, it depends, it's parameterized by element G of SL2, but it's a 4x4 matrix with components mu and nu. Explicitly given by 1/2 eta nu rho trace sigma mu G sigma bar rho G dagger. This is how this matrix looks like.
Excuse me, from where does the last formula come from?
I will explain once again. So what I have done, once again, watch what I'm doing. So I said x prime mu transformed.
What you're writing, what you were writing is from the left.
Yes. From the left.
Okay.
What does it mean?
Yes.
Okay. So trace x capital prime sigma mu, right? So this formula allows me to express my transformed coordinates via transformed 2x2 Hermitian matrix X. Now what I do, I substitute the definition of what this transformation is on X. This is G X G dagger sigma mu. Now what I'm doing, I substitute here X itself, where the coordinates of the original four-dimensional vector. And this is eta rho nu. How I write it? Sigma bar rho x nu. So I substitute it in. So when I substitute it, here sigma bar is a matrix. For each row, it's a 2x2 matrix. But eta rho nu and x nu, these are just numbers. I can take them out of the trace. And so I'm writing 1/2 trace G sigma bar rho G dagger sigma mu and eta rho nu x nu I'm taking out of the trace. So what we see then is that what is written down here in this formula, what is written down here is the object which has a form of the Lorentz transformation of some matrix lambda, which has index, say, mu and nu, acting on the original vector x nu. Over index rho, I'm summing up, and indices mu and nu, they are here. Here you see index mu, and here you see index nu. And mean index mu is free as index on the left-hand side. And so from here, by comparing this formula with this one, I can find actually what this lambda mu nu is.
So you are trying to embed SL2 to the SO
Yes.
plus 1,3, okay.
Yes, that's what I'm doing, exactly. So from here, you see that by comparing, you write the formula for lambda mu nu, and lambda mu nu is an element which will be is a now 4x4 matrix for this indices mu and nu, but it's parameterized by an element G of our SL2C, and it's explicitly given by the following formula: 1/2 eta nu rho or rho nu. Metric is symmetric, so it does not matter how you write it. Trace, and then also under the trace you can put sigma mu by using cyclicity of the trace on the first place. Sigma mu G bar rho G dagger. Okay, so this is the formula how now Lorentz transformations are realized via elements of SL2C. So in fact, so what this formula is telling us is that there is a map. It gives us a map from SL2C to group SO plus 1,3. Why I'm saying SO plus 1,3? This is because First of all, if you restrict yourself to lambda 0, 0 component of this matrix, putting here 0, 0, you see what I'm getting is 1/2 eta 0 rho. But since the metric is diagonal, that means that in order to have non-zero, I mean, there will be only one component of rho equals to 0. And therefore here I will have sigma 0 for index mu and also 0 for rho. And so I will be getting this formula here. Eta 0, 0 is 1. Sigma 0 is an identity matrix. So therefore, this is given by 1/2 trace G dagger. And this is a positive expression. So this is bigger than 0. And therefore, what you are realizing by means of this construction, you're realizing the transformation, which is nothing else as as orthochronous transformation, right? So the transformation which I'm doing is orthochronous. And also concerning the determinant, so I would like also to prove that this transformation is proper. That means I have to prove that determinant is equal to 1. You can easily compute by using the definition of lambda mu, the determinant, and you will find that determinant of lambda will be reduced to determinant of G. So please do this little computation to show that this is determinant of G multiplied by the determinant of G dagger, but since each determinant is equal to 1, you get 1. So this means that indeed you are realizing proper orthochronous Lorentz transformation in this way. What is actually very interesting is that this map from SL to C to SO plus 1, 3 is a map 2 to 1. So this map is 2 going to 1, which means that in fact you have two matrices of SL to C which go to one matrix of Lorentz transformation. And you see it because elements G and G minus G, which both belong to SL to C. If G belongs to SL to C, then minus G is also an element of SL to C. These matrices G and minus G go to one element of the Lorentz group because the corresponding Lorentz transformation, you see it's quadratic in these elements G and G dagger. So if you change G to minus G, the matrix lambda, which you construct in this way, will not change. It's a one and the same matrix. And so this means that we have this map 2 to 1. So two elements of SL to C go to one element of SO plus 1, 3. And moreover, it is known that the group SL to C is simply connected. Simply connected, while SO plus 1, 3 is not simply connected. Not simply connected. And what does it mean, simply connected? If you consider SO plus 1, 3, say, as a topological manifold, and you consider a closed loop and in SO plus 1, 3, the fact that it's not simply connected means that this loop cannot be contracted to a point all the time returning inside SO plus 1, 3. In other words, in SO plus 1, 3, there are uncontractable loops and non-contractable loops. Non-contractable loops. Non-contractable loops. So in a way, SO plus 1, 3 looks like a circle. So if you consider a circle, which is the simplest group U1 by multiplication, so unit circle, then if you consider any loop, then you realize that you cannot contract it because this loop, say for instance, winds this U1 several times, and it cannot be contracted to a point, right? And so this manifold of such a type, which contains non-contractible loops, is called not simply connected. And when any loop can be contracted to a point, returning all the time inside a manifold, then such a manifold is called simply connected. And now our Lie groups, they are manifolds, and it turns out that SO plus 1, 3 is not simply connected one, while SL2C is mathematically known to be simply connected. And in fact, what we are discovering here is that SL2C represents a simply connected double cover of SO plus 1, 3. So it covers it, and it's simply connected. It covers it 2 to 1. So if you allow me to draw it in this way, then SL2C can be drawn like this. So it goes around, and it turns into itself in such a way that, say, two elements.
So for simply connected, can we say that it is directly proportional to the number of turns?
Yes, it's related to the fact that there is a non-trivial center. And the map 2 to 1 means that two elements of SL2C are mapped to one element of SO plus 1, 3. So this would be my SL2C, which is this double cover. And two elements, say G matrix and matrix minus G, they are mapped to the one and the same matrix lambda depending on G of SO plus 1, 3. And then SL2C is simply connected. Any manifold, any simply connected manifold which covers non-simply connected manifold is called a universal cover. Universal means that it's simply connected. Universal cover. So SL2C is a universal cover of SO plus 1, 3. Now, as an exercise, I would like to propose just for you to check that indeed the matrix lambda mu nu, which is constructed in this way here, which is constructed according to this formula here, is indeed a matrix of Lorentz transformation by checking that it's preserved, that it preserves the Minkowski metric. It means that you need to take Minkowski metric eta mu nu, and you need to apply to it Lorentz transformation, lambda mu rho, lambda nu, say lambda, like this. And then you just compute this expression here by using this formula, by plugging for lambda mu nu this formula, and then you have to find out that what you will obtain here will be eta rho lambda. But in fact, we have shown this already, I mean, in a simple way by just noting that transformations of the type we are considering, they preserve the determinant, and determinant is a 4 interval. And so in this way, we know that this is Lorentz transformation, but once again, you can check it quite explicitly by just performing the calculation of this type and showing that if you directly, with this matrix lambda, act on the Minkowski metric, then you obtain the Minkowski metric back. Yeah, so this would be a very direct proof that this matrix lambda is a matrix of Lorentz transformation. Okay, that's in principle all I wanted to tell you, I mean, in the first approximation about Lorentz and Poincare groups. We will be returning to this subject again during the course. But now let me go on to the Noether theorem. But if you have questions about Lorentz or Poincare group, please ask.
So this type of symmetry we see only in Minkowski spacetime, right?
Yes. No, since far away from stars, our space-time looks like a Minkowski space, then the most important group of symmetries of quantum field theory is Poincare group, which includes Lorentz group and four-dimensional shifts. Okay.
So is there any general symmetry also for any type of background?
Yeah, so in general, if you have non-trivial background, which is not Minkowski space, then this background is characterized by certain metric, which you put on it. And this metric might have or might not have what is called isometries. And these isometries typically would provide a symmetries of a quantum field theory on a curved background. When your background is not flat like Minkowski space, so you consider particles, quantum particles, not in Minkowski space, but say quantum particles in the background of black hole, right? So this means a very curved space-time. And of course, for very curved space-time, the background is different, the metric is different, and the possible group of isometries, the group of which preserves the metric, will be, of course, different from Minkowski one. But in fact, for each manifold, you can define the notion of a tangent space. So at each point, you will have a tangent space. So even if you have a curved manifold, you have a tangent space. And then in this tangent space, you will get a group of transformations of vectors, of tangent vectors, which are attached to this space. And this space is linear, and therefore you will have a group of linear transformations. And if this tangent space is supplied or inherits a Minkowski metric, then this will be a Lorentz group of the tangent space. So Lorentz group becomes local. You associate it to a tangent space, but not to the whole manifold. Moving from point to point, you will have different sort of local Lorentz groups in this case. And in general, if you have non-trivial metric, you can talk about diffeomorphisms which preserve this metric. And these diffeomorphisms which preserve the metric on a given manifold, they are called isometries. And they form the group of isometries. And then, as I said, in quantum field theory, the isometry group becomes an important group to discuss. It will become an important group of symmetries. But in Minkowski space, we deal with Lorentz group.
Okay, thank you.
Okay. Now, if you don't have questions, we come to the next subject, a very important subject, namely to Noether's theorem. Noether's theorem, which has been established by Emmy Noether in 1918. And why it is important, that is because this theorem relates symmetries to conservation laws. And if you are given a dynamical system, then a special role is played by the so-called dynamical invariants, or quantities which are invariant with respect to dynamics of the system. And sometimes these dynamical invariants, or very often these dynamical invariants, they are called conservation laws. Dynamical invariants, and the same as conservation laws. I will use both terms, conservation laws. And what it means is that if you have some dynamical system, you have, for instance, a system of particles, they are characterized by coordinates and momenta, And when your dynamical system develops in time, the coordinates and momenta undergo changes. So they change their values with the time. But out of these changeable variables of coordinates and momenta, you can create some complicated, maybe simple quantities which stay invariant while time develops. So axes and p's of individual particles or individual constituents of the system change with time, but dynamical invariants remain unchanged. And for this reason, they are called conservation laws. And if you want to describe your dynamical system, it's not enough to know just the solutions of the equations of motion. So in other words, how individually axes and p's, say coordinates and momenta, develop in time, but it's also important to be able to express the basic physical characteristics of a system, like for instance, conserved energy, conserved momentum. We're solutions of these equations. So you need to know the energy and say momentum or angular momentum of a system as a whole. And you need, for this reason, to be able to find expressions for these quantities like energy, momentum, angular momentum, and so on, in terms of individual dynamical coordinates and momenta, in other words, phase space variables of your system. And this goal is precisely achieved by means of Noether's first theorem, which I would like now to formulate in the context of the field theory. So Noether's theorem tells the following. So let the action of a dynamical system be invariant up to a boundary term with respect to a finite parametric that is dependent on S constant parameters continuous transformations of fields and space-time coordinates. Then first, there exist S linearly independent currents G, J, mu, N, where N runs from 1 up to S, with divergences equal to certain linear combinations of Lagrangian derivatives. And the second, on shell, as people say, on shell that is on solutions of equations of motion, these currents are divergenceless. These currents are divergenceless. These currents are divergenceless. This means G mu n is equal to 0, and they give rise to dynamical invariance or conservation loss, dynamical invariance, which are conserved functionals, of fields and their derivatives. This is how the Noether theorem is formulated. So if you have an action which is invariant up to boundary term with respect to continuous S-parametric transformations of fields and coordinates, then there exist S linearly independent currents, J mu, with divergences proportional to Lagrangian derivatives. And on shell, these Lagrangian derivatives vanish because these are equations of motion, and therefore these currents become divergenceless, and they can be used to construct dynamical invariants, which are conserved functionals of fields and their derivatives. So this is how the Noether theorem is formulated. And these symmetries of the action, which leave the action invariant up to a boundary term, they are called variational symmetries. So this kind of symmetries, they have a special name. So symmetries which preserve the action up maybe to a boundary term, these symmetries are called variational symmetries. Because there are other types of symmetries which are not of this type, which are not variational. And the symmetries we are talking about in the Noether theorem, they can be then formulated in the following form. So they involve transformation of the coordinates. So coordinate x mu goes to x prime mu, which is function x prime mu depending on fields. There can be several fields. Fields might have a different nature. They can be scalars, vectors, tensors, and so on, and the original coordinates. So yeah, let me not write index x here of mu of x. Just say x prime mu is a function of all fields and all coordinates, and together with this, I also need a transformation of fields. Just a second. Which are of this type. Fi on x goes to phi I on x goes to phi prime I on x prime, which are transformations depending also on all fields and all coordinates. Index mu, we assume that we are working in d dimensions, so we allow index mu to run 0, 1 up to d minus 1. Now the derivatives of the fields under these transformations will change accordingly. So d mu on phi I will go to d mu prime on phi I prime. So we are changing simultaneously coordinates and fields. So in general, such transformations can be rather non-trivial, because you are not only transforming space-time coordinates, but you say that you are also transforming fields. And moreover, in general, you may require even space-time coordinates to be transformed by involving fields. So these transformations may be quite non-trivial. So let us now prove this theorem. Let's start with the proof, how we can do that. So first of all, the theorem requires that we consider symmetries of the action up to a boundary term. And it means that if we take our action functional, which is an integral over d-dimensional space-time of Lagrangian density, then in the new coordinates, the action will look like integral of dx prime of new coordinates of the Lagrangian density. And we are in d dimensions, so let's specify it in the measure like d-dimensional measure in new variables x prime. And in the Lagrangian density, we substitute our transformed fields, phi I prime on x prime here, and derivatives d mu prime on phi prime I on x prime. Now, we also will integrate, since we make this transformation of coordinates, we also integrate over the image of the original region omega under this coordinate transformation. So originally we have some integration region omega, which can be arbitrary, or which is arbitrary. And under this transformation x to x prime, it's mapped to some other region, which we call omega prime. And then, so this is action S prime under, we perform such a transformation. And the condition of the theorem requires that this is given to the old action. So that means the integral dx Lagrangian on the old fields phi I x I, d mu phi I x depending on x, up to a boundary term, which means that this can be changed by, say, adding up the total derivative d lambda mu over dx mu. And you remember in the last lecture, we have discussed that adding such a derivative where lambda mu is a function of fields phi does not influence equations of motion. So variational symmetries allow the change of the action up to a boundary term. So by up to the boundary term, it is this boundary term which Noether theorem allows. This is boundary term. Okay, so this is a condition, so to speak, required in the Noether theorem. Invariance of the action up to the boundary term, and this invariance must be action is evaluated over arbitrary region omega, arbitrary volume omega. This is very important, that omega in the formulation of the Noether theorem should be arbitrary. Okay, since omega is arbitrary.
Excuse me, I have a question.
Yeah.
So last time you say that the boundary term won't change the equation motion, but there's a constraint on it. It should only contain the phi, but not.
Yes, and this is the same here. So I consider this lambda to depend on phi only. It is the same.
Yeah, but the lambda comes from the coordinate and transformation and the variation over.
Yes. So
phi. How can we guarantee?
We are not guaranteed. It's a requirement. So transformations which we are considering must be transformations of such a type that then this condition here is satisfied. Okay.
Okay.
This condition is satisfied. In fact, I don't think that for the Noether theorem itself, it is important that this lambda mu depends only on phi. In general, of course, lambda mu might depend on also on derivatives. But the problem is that in this case, this addition of the boundary term does not preserve the physical requirement to have a unique solution of the standard Cauchy problem, because then the new Lagrangian would involve derivatives higher than the first derivative, right? And that's only for this reason this lambda mu is required to depend on phi. If you don't want to change the Lagrangian, the physical nature of the Lagrangian, then you have to restrict the boundary terms in this way. But I think in Noether theorem, even that is not important. Even that is not important. Noether theorem is just telling you that any boundary term is allowed. If it's a boundary term, that means it's a total derivative, which you may add to Lagrangian densities, and this is enough for the Noether theorem to be true. I think in Noether theorem, it's not required that it's a function of phi. Okay, so how we can proceed? I mean, what we want to do now is we want to use arbitrariness of this volume omega and to compare the integrands of these two integrals. And for that, we can make a change of coordinates here and pass to integration over the original variable x over the region omega. And you know how to do it. For that, under the change of coordinates, you use the Jacobian. So you introduce the Jacobian, which is a determinant of the Jacobi matrix, dx prime alpha over dx beta, and determinant, multiplied by the measure ddx. And so this is measure ddx prime. Under the change of coordinates, this is the way this measure will be transformed. And so then you will have two integrals over the same volume omega. And since omega is arbitrary, you can change it arbitrarily. The left-hand side should be equal to the right-hand side. And then this is only possible if the integrands are equal to each other. And so the condition of the equality of the integrands then is written in the following way. So L Lagrangian density depending on phi prime on x prime. Let me not to write this index I. This index I, it can be there. It might be even tensor index or index numerating fields. That means it can be many fields, does not matter. So what you get is then this condition that Lagrangian density on the transformed fields multiplied by the Jacobian, like this, must be equal to L on phi on x d mu phi plus the total derivative d lambda mu on dx mu. And once again, this follows from arbitrariness of omega. Okay. Now the transformations we consider infinitesimal version of this equation. So this means that we need infinitesimal transformations. X mu goes to x prime mu, and infinitesimally what we do, we add to x mu a small variation of x mu, and this is, if you wish, infinitesimal version of this transformation here, Also for fields, infinitesimal version phi I on x. Again, index I can have any nature. It can be a collection of tensor indices or index enumerating different fields. Phi I goes to phi I prime on x prime, which is an old field, phi I on x, plus a variation delta phi I on X. And again, here this addition to phi I is an infinitesimal version of this transformation law here, global transformation law here. Now, what we need to do also, we need to somehow parameterize these transformations with the help of individual parameters. As you remember, now in the Noether theorem, we were talking about S-independent constant parameters, which parameterize these transformations. And so these transformations are linear and continuous functions, infinitesimally. They are continuous linear functions of these parameters. And therefore, we can write that delta x mu is given by sum over these parameters, which I denote by as epsilon n. So sum goes over n from 1 to s, x n mu multiplied by epsilon n. So this epsilon n are parameters, and they are constant in a sense that they do not depend on space-time points or fields. They're just numbers. They are numbers. No, and this x and mu, these are quantities which describe response of x mu on this change by infinitesimal parameters epsilon n. And also for the fields, we can write that delta phi I on x is given by response of these fields, phi I capital, depending on I and index n. So phi I comma n multiplied by epsilon n, and n is running from 1 to s. Okay. So this x capital and phi capital, these are responses. Responses of response of coordinates and fields. Coordinates and fields on infinitesimal transformation. Infinitesimal transformation with parameters epsilon n. Now, let's look at how Lagrangian density transforms under symmetry transformations. And for this reason, we need first to consider phi I prime on x prime. So infinitesimally, first we write it in the following way. So phi I prime, and I substitute what x prime is. And x prime is x plus delta x. And this now I can expand in a Taylor series in the following way. I write it as a fi prime on x plus derivative d mu, so derivative with respect to x, of phi I prime on x delta x mu, plus higher order terms, which I'm not interested in because I'm considering infinitesimal transformations. So transformations up to the first order in epsilon. And if I continue, then I write fi prime on x plus d mu phi I prime on x. And now I substitute delta x mu. And delta x mu is x capital response n mu multiplied with epsilon n plus higher order terms. Now you see that phi prime is different, will be different from phi I also by order epsilon. But one order epsilon is already here because of delta x mu is of order epsilon. And this means that I will not a mistake at leading order in epsilon if I replace here in my derivative phi prime with the original field phi I. In this case, I will not any mistake at a given order epsilon because the difference between phi prime and phi is of order epsilon, and so it will contribute to the order epsilon squared. So somewhere here in the terms which I'm not interested in. So this is how this transformation looks like for fields phi. And at this point, it is important to realize that this derivative delta, well, not derivative, but variation delta, this variation does not commute, variation which we apply to the field phi, this variation does not commute with derivative d over dx mu. And why is this? Because variation delta encodes an effect of both change in coordinates and fields. This variation is due to both the change of the form of the field and also due to the change of the argument of the field. So this variation delta phi encodes both variation of coordinates and the variation of the form of the field, So in order to distinguish variation of the form from the general variation, which also involves variation of the coordinates, we introduce the variation of the form of the field, which I denote by delta with a bar. And by definition, this is phi I prime on x minus phi I on x. So in other words, I watch how the variation of the form of the field changes, keeping this field at the one and the same point. So space-time point is kept untouched. And I'm considering the difference between primed field and unprimed field, but at the one and the same space-time point. You can find what this variation is, the following thing. So this is phi I n minus d mu phi I x n mu multiply with epsilon n. And I throw away again higher order terms. So this is how variation of the form of the field looks like. So let me write down that this is variation of the form of the field. So in fact, what I have done, I said that this phi prime on x prime here on the left, this is phi I on x plus delta phi I, right? And so now I compare what is on the left, so here, with what is on the right. So on the left, I have phi I on x plus delta phi on I. By delta phi is given by this formula here. So this is therefore phi I n phi I comma n epsilon n. And on the right hand side, I get phi prime on x plus d mu phi I x n mu epsilon n, up to leading up to higher order terms, which I'm not interested in. Then this is an equation, and from here I see that I can compute variation of the form by putting this field to the right hand side and derivative to the left hand side, and then I'm getting, by definition of the variation of the form, an expression phi prime on x I minus phi I on x as phi I n response of the field to the variation minus d mu phi I x and mu multiplied by epsilon n. Okay, so this is how variation of the form looks like. And now you see that variation of the form actually coincides with the variation, full variation, only if delta x mu is equal to 0. In this case, there is no such a term as x and mu, because this is a response of x's on the variation of coordinates, and therefore if the variation coordinates is 0, there is no x and mu, and then variation of the form coincides with the full variation of the field. So now we can compute the variation of the Lagrangian density, and for that we consider now the Lagrangian as a function of the variable x. So the new Lagrangian density is lambda prime on x prime is equal to Lagrangian density on phi prime on x prime, comma, d mu prime phi prime on x prime. So this is the Lagrangian density, which I consider now as a new function of the coordinate x prime. So it's an old Lagrangian density evaluated on the new coordinates and new fields. Then we have Lagrangian density primed is equal to Lagrangian density old on the variable x plus derivative of the Lagrangian with respect to x mu multiplied by delta x mu. But what is this? I can write it as a Lagrangian density plus Lagrangian density prime minus Lagrangian density. So I added Lagrangian density and I subtracted. This gives me variation of the form of the Lagrangian plus this total derivative, this one, dl over dx mu delta x mu. And the variation of the form delta bar L x mu is computed in the usual way as any variation. First, I differentiate the field with respect to Lagrangian with respect to the field phi I, and then I take variation of the form of this field phi I. Then I differentiate the Lagrangian with respect to derivative on phi I, and I take derivative with of delta bar phi I, and here I use the fact, in fact, that variation of the form commutes with the derivative, with the space-time derivative. And then this is very important, that this is exactly allowed me to move this d bar, delta bar, close to the field phi I, to pull it through the derivative d mu. So these two things commute with each other. And this gives me the following. So this I can write as a dl over d phi I, and here I will put the derivative d mu here for the price of adding up a total derivative term. So I write it as a minus d over dx mu acting on dl over d mu phi I, like this, multiplied by delta bar phi I, plus total derivative dx mu acting on Lagrangian derivative d mu on phi I multiplied by delta bar phi I, like this. No, and that's basically it, except one thing. Well, here you see that I'm already obtaining what is called Lagrangian derivative. The last thing to take into account is the integration measure, the infinitesimal expression for integration measure. So I think on the next lecture, I will show you that the integration measure infinitesimally is given by the following expression. So this is a determinant of the Jacobi matrix, and infinitesimally I need to compute this derivative. So delta x alpha yeah, so I need actually to write it in the following way. This is d over dx beta x alpha plus delta x alpha, and determinant. So I need to compute the determinant of the matrix delta alpha beta plus d delta x alpha over dx beta. And you may see that if you want to restrict yourself to the leading order in epsilon, then this expression in the leading order gives you 1 plus divergence d over dx mu of delta x mu plus higher order terms. So this is a leading term in epsilon, but there are other corrections which I am not interested in, higher order terms in epsilon. That's basically it. Now I return back to the original equation, which is required in the Noether's theorem, namely to this one. So this formula here. And consider its infinitesimal version. Now I will replace Lagrangian by Lagrangian plus its first variation. I replace the measure at leading order in epsilon, and then I compare it to the term which is on the right-hand side. So let me then write what we will be getting in this way. Maybe I have to do like this. This is the last step, and then we will finish. So what I will be getting is the following: Lagrangian plus variational derivative delta bar phi I plus d over dx mu Lagrangian d mu phi I delta bar phi I plus dot 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 plus derivative of the Lagrangian over x mu delta x mu. Then this should be multiplied with the Jacobian at leading order. This is 1 plus d over dx mu delta x mu plus higher order terms. And on the right hand side, we still have Lagrangian, original Lagrangian, plus the total variation of the total derivative term infinitesimally. So we vary it according to how fields and coordinates vary. So you need now to open the brackets on the left, collect the terms at leading order. So as I said, delta lambda mu is understood as lambda mu n multiplied by epsilon n as well. So leading order in epsilon. And after collecting the terms of order epsilon, you will get the following expression: d over dx mu, total derivative acting on d Lagrangian d mu phi I delta bar phi I, variation of the form of the field, plus Lagrangian delta x mu minus delta lambda mu. This is on the left hand side, and on the right hand side you get up to the minus sign the variational, the Lagrangian derivative, which has this form: d mu phi I minus d Lagrangian over d phi I multiplied by delta bar phi I. So this is how this expression looks like. And this is the Noether's theorem. From here, you read off that there is a current, J mu, which is d Lagrangian over d mu phi I delta bar phi I plus Lagrangian delta x mu minus delta lambda mu, which divergence vanishes on equations of motion, or if you're talking just about this expression above, then this is telling you that the divergence of this current J mu is given by a linear combination of Lagrangian derivatives epsilon I And this linear combination involves this variation of the form of the field phi I. So index n is introduced in the following way. So now if you plug in these variations explicitly, a variation of the form of the field and variation of the coordinates and variation of lambda mu, then you will see that since parameters epsilon n are independent, for each of these parameters, you will have a conserved current. So this conserved current, G mu n, where index n runs from 1 to s, will be given by the following expression, minus d Lagrangian over d mu phi I, response of the field phi I n minus d nu phi I x nu n, so response of coordinates, multiplied, okay, so response of coordinates minus Lagrangian multiplied by xn mu plus lambda mu nu, this boundary, the expression coming from the boundary term. So this is an expression for the so-called Noether current. This is how the Noether current looks like. And on equations of motion, in other words, on shell, as people say, on shell, all Lagrangian derivatives are equal to 0, which are equations of motion. These currents are conserved. In other words, their divergences is equal to 0. It's equal for any n running from 1 to s. This is basically completes the proof of the Noether theorem. The only point which I did not explain is the construction of the dynamical invariance, which comes out, which relies on the divergentless currents. But this I will explain in the next lecture. So this last point, let's leave it to the next lecture. Okay, with this I would like to finish, and if you have questions, please ask. I think you need time to appreciate a bit how this derivation is done. For that, you may look again at the recorded lecture of today, and you can also read again through my lecture notes to appreciate all details of this derivation. Once again, this is a very important theorem. It's a cornerstone of classical mechanics and also of quantum field theory, quantum mechanics, quantum field theory, because it allows you to construct the conserved quantities and relate them to symmetries, to variational symmetries of your action, describing your dynamical system. Okay. No questions? Well, once again, look through the lecture notes, and you might still have questions for the next time. So please, if you don't understand something in this important derivation, please ask me next time. Okay?
Okay.
Otherwise, I wish you a pleasant day. Thank you very much.